Welcome once again. I will start with introducing myself. My name is Mateusz Sandrzak. I am a structural engineer here at SDC Verifier, and today I will be your host. And we are going to discuss a topic of hidden structural risks in wind turbine support structures. So, without any further ado, let's start by checking today's agenda. And as you can see, first we are going to discuss wind turbine supports and what real-life problems are associated with this kind of structures. What type of failures can we expect, and what are the usual problems? And then we are going to focus on what design assumptions are often made by engineers while designing such structures, and what is in reality. So what are the differences? And it also can cause some problems in the future with the structure. And then after that, we are going to focus on what loads are acting on such structures. And then we are going to discuss why global checks alone are often insufficient. And for this section, we are going to compare two models that I prepared. One is fairly a simple beam model, and the second model is a more detailed plate model of the support structure. And we are going to basically discuss the outcomes of both analyses. In the meanwhile, while we are going to discuss all of these points, I will show you how with the help of SDC Verifier, we can solve some of the issues that we face along, and how we can basically execute the checks from A to Z, from the start to end, to correctly verify our structure. At the end, I would like to spend a few minutes to discuss our platform is SDC SAM, which is a platform to monitor and check the condition of your structures through the web. So that would be it. I hope you are interested. So we can start with a few words about SDC Verifier. If someone is new there and never attended our webinar, we are a company which was founded in 1998 by Wouter van den Bos. So we have approximately 28 years of experience in engineering. And as you can see, we started in Netherlands, but we also expanded, and currently we have 3 offices. Apart from Netherlands, we have an office in Poland, and we have an office in Ukraine. Our company can be divided into two, let's say, sectors. First one, this is the developer sector, which is responsible to developing basically the software that we are that is used for FEA calculation. And the second one, this is the consultancy, where we basically execute projects with help of the SDC software, and we deliver it to the client. As you can see, our team consists of more than 40 people. Our developers are currently working on 5 softwares, and also on what I mentioned, the SDC SAM, which is the structural asset management system. We have over 1,000 happy users worldwide, so I think we are well trusted. Okay, a few introduction words, and we can start with today's topic. Wind turbine support structures and real-life structural problems. As you know, wind turbine support structures are one of the are critical component in the modern wind energy system. They have to support large rotating machines, which are operating under continuously changing environmental conditions. So these structures must safely transfer the loads, which are the aerodynamic loads and environmental loads, into the foundation systems, while also they have to maintain the structural integrity throughout its lifetime, which is usually for this type of structures, this is usually between 20 and 30 years, sometimes even 40 years. Although these structures are designed using a lot of design codes and standards, advanced simulation methods, and there are a lot of verification procedures, real-life structural problems still occur. In many cases, the issue is not insufficient global strength, but rather slow development of fatigue damage in some crucial details. And as a result of millions of load cycles from the wind, from the waves, and so on, this damage might initiate and evolve before it is even visible from the global level. And over time, all these zones, all these damage zones can continue to grow, and eventually it can become a real problem, causing big cracks, which will then lead to expensive repairs or can even cause structural failure. And this is why identifying and verifying these zones early is very important. So the next question becomes, what actually causes these hidden structural risks? But before we discuss the actual loading environment, it is important to understand one thing, that during design, we usually, or even always, we simplify reality. So numerical model and the FEA models are based on assumptions that help us make the problems computationally manageable. So we often assume simplified loading conditions, ideal geometry, constant material parameters, some simplified boundary conditions, and so on and so on. However, in reality, it might be different. So, for example, wind velocity is constantly changing due to the weather. Also, it can act at different angles. It increases with height, which is often not included and not taken into account by engineers. Also, material degradations occur over time due to fatigue and corrosion, causing reduction of thickness and weakening of material. Weld imperfections can also influence stress distributions and so on. Also, in offshore structures, soil stiffness and support conditions might also change during the structure's lifetime. So, as you can see, over the years of operation, the actual structure and its behavior is different from the assumed simulation model. And these things can lead to hidden structural damages. Also, what is worth mentioning here, what we will discuss later, is basically the representation of your model. If you simplify it too much, if you don't include some crucial details, some crucial connections, maybe some welds and so on, basically you might end up with results that are passing your standard checks, but reality might be different since it is not included there. So it is, as I mentioned, we will cover it later, but it is important to represent your structure how it is in real life. So let's now take a look how these structures are basically loaded. So the main loads that are acting on the wind turbine support structures are environmental loads, and the primary source is aerodynamic loads, which are generated by the wind. So wind is acting on the rotor, which creates some thrust forces and some moments, which are then transferred through this tower to the support structure. And at the same time, the wind is also acting on the support structure itself. Other than that, the extra forces that are also there are caused by water. So you end up with wave loading, with ocean current loading, and some hydrostatic pressure. And all these mentioned loads do not act independently. So many of them, in this case, all of them, they act at the same time simultaneously. And their magnitudes and directions are also constantly changing. So wind velocity, as we previously mentioned, changes with its height. Wind and wave loads change its magnitude, may act from different directions, and so on. And as a result, engineer must consider a very large of possible loading cases to make sure that all possible scenarios are included and verified. And because these load cases are highly variable, as mentioned, and cyclic in nature, and they are one of the main reasons of fatigue damage that in these types of structures. So as we mentioned about the loads, the next issue appears: how do you accurately apply those loads in your FEA model? And here comes SDC and our specific loads. Besides some basic load definitions, as you are familiar with, for example, some body loads, some nodal loads, you can apply some extra loads in SDC, such as wind load, buoyancy load, and wave load. All of these mentioned loads, they are applied as a pressure to the structure. And firstly, let's see the wind load. So on the left hand side, you can see the window where you basically set up the wind load. You can apply it in different directions, also at different angles, and of course you can make either a selection where you want to apply it, or you can, for example, set where is the ground level. Since this bottom part is going to be under the water, it will not be subjected to the wind load, only this top part, as you can see. And as you can see, the two inputs that are required, this is the height in the vertical direction in your model, and then either a pressure or wind velocity. And on the right side, you can preview how this pressure changes with height of the structure. On the right side, you can see the vectors, how the force is applied to the model, and in this case, the wind is acting in the plus X direction. Also, what I didn't mention, you can set up drag coefficients in the model based on different properties and so on. So you can set it up for all different sections if you are working with beam models or for plate thicknesses. Then there is the buoyancy load and wave load combined together. So again, on the left side, you can see the setting window, what needs to be inputted to create such load. So first of all, what you need to specify, besides some standard values such as density, gravity, and so on, you need to define where is the water line for your structure. If you know this height, then you can automatically apply it, as in this case. But if you don't know it, it can be calculated approximately by SDC with using the mass of the structure and its coordinate system. It will basically find where is the balance between the pressure of the water and the weight of the structure. What you can also include, which is not necessary, but in this case we also include, this is the wave, and here you need to input some parameters, as you can see on this right bottom graph, such as height and length. You can also apply phase and angle if you want to check such conditions. And on this top right picture, you can see how the pressure is applied to the model. And on the legend, you can see this is pressure in pascals. Coming up next, why global checks alone are often insufficient. As you know, when we are building an FEA model, what we discussed before, the first step is deciding how to represent the structure and what type of elements you should use. In the early stages of the design and during some global verification, simplified beam models, such as you can see on this left side, are commonly used. The left one, it is simply just beams with thickness on off, and on the right side you can see with thickness on. And what are the pros and cons of such simplified beam models? They are very effective to understand the global behavior of the structure, how it behaves, how it deforms, where can you expect some stress overshoots, and so on and so on. What are the pros of it also is that these models are very quickly to build, very easy to build, and the computational cost is very low, and it makes them very efficient for the preliminary results. However, this approach also has some limitations. In particular, as you can imagine, as you can guess from these pictures, modeling of some detailed connections is not possible, especially in regions where you have some complex joints and connection. And as a result, some local effects might be underestimated or completely neglected. And on the right side, on the other hand, we have the detailed plate model. These allow you for a much more detailed representation of the structure. They can include some complex connections and some local features. This makes them more suitable for accurately representing the stress distribution and the local behavior. However, as you can again imagine, there are some cons, and that it is both very time consuming to pre-process the model. It means to prepare the geometry, mesh the model with great quality, and so on. And it is also high in computational cost. It will calculate simply way longer than beam element due to the elements that are used. So yeah, it is important to decide with which one you want to start. Let's check more in detail this beam model. As you can see, this model is very simple. It has a few sections. I think it has around 300 elements only. As you can tell, it's not a lot. And all the connections are very simplified because all the beams are just simply connected to one node. As you can see on the right side, for all of these beams, tube sections are used. On the other hand, we have the plate model. As you can see, very detailed with very fine mesh. I think this model has around 600,000 elements. And as you can see, all the connections are in detailed modeled nicely. If you look inside of these tubes, then you can see all the stiffeners are also included and modeled over here. They are welded to the structure, so all the welds are going to be taken into account in this verification, which can have a crucial, which they can be very crucial for the verification of this kind of structures. So we can move on. Before we check these structures under some standards, maybe some fatigue standards, some plate buckling standards, and so on, it is important to understand that all of these checks are not performed on finite elements, but rather they are performed on structural items. It means on welds, on beams, and on some plates. So, for example, on this left side, on top left side, you can see a picture after recognition of all the welds in the model. Basically, with one click, all the welds were recognized, and you can see them all of them in the table. So all the dimensions are written, such as length and even plate thicknesses and so on. It is also important to mention here that if your standard specifies different weld classification for non-welded parts, welded parts, or maybe even weld intersections, all of these things are automatically recognized by this recognition tools. So all welds are divided into welded and non-welded parts. Where they intersect, they are also taken into account. Coming up next, bottom left picture, you can see this is the panel recognition. For example, if you wanted to execute some panel buckling, then you need to perform this panel recognition. Again, as you can see in the table, while doing this recognition, all the parameters such as length, such as width, such as thicknesses, and so on, and all the necessary things are automatically written. Then top right corner, this is the beam member check. This is the beam finder recognition tool. This is used for some beam member checks, buckling, and so on. And basically, it recognizes all the beams in the model, and also it stores what buckling length they may have in two different directions. And the last one on bottom right, you can see this is the joint recognition. So basically, these are the areas where your beams are connected. And as you can see, you can have different types of joints depending how they are connected. If they are connected in one line, then these are 1D joints. If they are connected in one plane, they are 2D joints. And if they are connected in multiple planes, then these are 3D joints. For all of these recognition tools, you can edit them manually, edit parameters manually, or include some welds, some panels extra if they were not taken into account, or for example, split panel into two panels, and so on and so forth. What you can also do without updating your model, let's say if you wanted to preview some results for a plate with different dimensions than it is right now, you can simply edit them in the table, in the recognition table, and rerun the check and see the outcome without needing to update your FEA model. Okay, let's go forward. So as we did all these recognitions, now it is time to set up our standard. And since we are talking about offshore structures, specifically about this wind turbine supports, then here for this purpose I used DNV RP C203 fatigue standard. And as you can see, if you open the standard wizard, here you need to basically define 4 options. First one, this is the environment, whether it is air or seawater. You can always, for part of the model, you can define different types. So for the part of the model, you can define air. For the part of the model, you can define seawater. And it is important to also mention that behind all of these types and options, there are numbers in the formulas. Then there is reference thickness, whether it is non-tubular or tubular. All these sections, all these options are strictly related to a specific standard. So I think we don't need to spend a lot of time over here. The one thing which will be relevant for all fatigue standards, this is the SN curve, the Weld classification. As you can see, it is very easy to apply Weld classification for all the welds and in different directions. You simply select all the welds that were recognized and you apply your classification in different directions. You can always also apply those classification on welded parts, non-welded parts, even some weld types are recognized. So, for example, butt weld, T-welds, and something, and stuff like this. And what was mentioned before, also the intersections are there. So let's take a look on the weld classification. In this case, we are going to analyze the detailed model, which is the plate model. And as you can see, in the X direction, which is the along its weld, our classification for all welds is C1. And in the case of weld intersections, it is D. And for the rest of the model, so for non-welded stuff, it is B1. As you can see in this close-up, you can nicely see that all of these intersections are nicely recognized and highlighted with this blue color. All these classifications, these are taken from the standard. Let's check the Y direction. Also, what I didn't mention regarding the weld finder, what it also does, as I'm explaining right now these directions, the X directions as shown before, it is along the length of weld, and Y direction, it is perpendicular to the length of the weld. What weld finder also does, it automatically reorientates the coordinate system for the elements in a way that these stresses are written in correct direction. Okay, so here you can see the Y direction classification. And the last one, which is needed, this is the XY. As I mentioned, you can apply different classification based on different quality of your weld and different standards that you are using. Coming up next, before we check the results, what I also wanted to mention that besides this DNV standards, the standard as I showed you, we have plenty more checks and standards. As you can see, over 50 of them currently. So we have standards such as ABS, ASC API, Eurocodes, and so on and so forth. So the list is quite extensive. They can be grouped into, as you can see in the bottom, as bolt checks, beam backing checks, static stress checks, joint checks, weld strength checks, and so on. What is also worth mentioning that for each of these standard, they are transparent, so you can preview all the formulas that are inside these checks. And for specific elements, you can check basically how all the values were calculated. So if you are curious about your value of your end value, so let's say utilization factor, you can preview how all the intermittent parameters were calculated along to check it. What you can also do is you can create your own checks on the basis of other check. So, for example, you can copy EN 13001 standard and slightly adjust the formulas up to your needs, and save it as some different standard, and you can use it for your verification. Okay, right now let's finally check some of the outcomes of performed analysis. As you can see, first we're going to take a look on this beam model, and as the model is very simple as we discussed, but you can already see that there are some zones where the utilization factor passes that doesn't pass the allowed criteria, so it exceeds the value of 1 since we are checking the utilization factor. As you can see on the right hand side, do not miss anything. We used another post-processing tool from SDC, which is the peak finder. So basically it highlights all elements which exceed the criteria you set up, in this case utilization factor of 1. So all of these elements do not pass our check, and you can nicely see them. So these are all the elements where you have these beam connections. What can you already tell based on this picture? Even though, yeah, as mentioned multiple times, a model is very simple, you can already have an idea where you can expect, how you can predict basically the behavior of the structure, and you can already in this beginning stages, you can already decide whether or not you want to, for example, model some connections more in detail, or you want to basically keep them as it is. And as you can see, the total utilization factor and the maximum value, it is 2.27 in this case. Let's check the plate model, and as you can already see, it is significantly worse. But doesn't mean it's worse. Maybe of course the outcome is worse, but it is way more detailed and way more realistic, since we represent the actual structure, how it is in real life. We represent the structural stiffness correctly by including all the stiffeners that are welded to the structure and so on. We end up with many overshoots, as you can see, due to millions of cycles of operation. On the right side, you can see all the zones basically that are exceeding these values. And just to take a look quickly and compare both of these, you can see in general, these areas are similar, and it is already it would be already a great idea at this stage to make a decision to model these connections in detail and investigate it. So after you are done with calculations, all the checks are performed and so on, what you can do, this is another tool of SDC, which is the automatic reporting. What it basically does, as the name says, you can create some automatic reports without a lot of work. So currently we have a few templates that you can use. For example, we have a template for model setup report. What this template already consists of, it is basically entire information regarding the setup of your model. So there you will find information about the model masses, what materials are used with its properties, what cross sections are used, what plate thicknesses are used, and so on and so on. So yeah, as I mentioned, everything regarding the setup of the model, also together with with load definition and constraint definition. We also have a second type of report, and this is the result report. It consists of already predefined some basic plots and tables to show the outcomes of results for all the loads, for all the load cases and load groups that are created in the model. You can always, both of these reports are highly customizable, so you can adjust whatever you want. You can exclude some of the stuff. You can include your own chapters, own texts, own image, maybe some custom plots if you wanted, some standard checks, plots and tables and so on. Basically anything you can imagine. Entire report from 100 to 0 can be done inside of here. And basically a few summary words, because most of this stuff, yeah, we already mentioned, we already discussed. So what is SDC Verifier? As I mentioned, this is the FEA simulation software where you can execute your project from the beginning to the end. So you can in here you can start by preparing your geometry of the model, then create mesh. You can apply the loads and create load combinations from these loads with specific factors, and then you can recognize structural items such as welds, such as beams, plates, and so on which then you are going to perform your standard checks. And as we mentioned, currently we have over 50 standards, and this list continuously grows. One of the tools that I didn't mention, this is optimization. We also have optimization where you can check different outcomes of your analysis based on different cross sections or different plate thicknesses without needing to update your model. And at the end, this is the reporting which we showed before. What is also nice to mention, as you can see, these arrows, and if in case you deliver the report to the client and then some adjustments have to be done, some modifications in the model and so forth, you can simply update the model, rerun the calculation, and regenerate entire report without needing to either set up your checks once again, set up all the plots, all the tables, and generate basically 400 pages of reports once again. Everything is already stored. You can simply reanalyze your model and generate everything, and you should be good to go. And we also have this SDC SAM platform, but I will talk about it in a few minutes. So as mentioned, we are currently having a few softwares. First one of them on which I was preparing all of these plots and results for this webinar. This is the SDC Verifier standalone. This is our main software, all-in-one solution, as it says. So basically here you can perform everything, as mentioned, from the preparation of geometry to meshing, applying loads, creating load combinations, then performing recognition, standard checks, and report. Everything can be done inside of this software. So basically, you don't need anything else to perform your projects. But then we also have some other softwares. This is SDC Verifier for ANSYS. How it works is it is basically an extension to ANSYS, and you calculate your models, perform your analysis in ANSYS mechanical, and then simply connect SDC to it, and then SDC is going to read all the results from the performed analysis on which it is going to perform the checks. And you can also obviously perform all of these recognition tools and display them in mechanical, and you can of course also prepare these reports. The same idea works for Simcenter 3D as for ANSYS, and it is also capable to work with Simcenter FEMAP. And the last topic for today, which I would like to discuss, and this is the SDC SAM. So what is SDC SAM? SDC SAM is our web-based solution, and it is used for basically inspection of your assets. So over there you can monitor the health, the state of your structures, whether the condition is great, doesn't require anything, or whether it is critical, it has to be inspected, or some action has to be done. So basically, after you perform your analysis, you have all your checks performed, you can import all of them to this web solution, SDC SAM, and you can have a look at all your structures from the phone, and you can preview all the statuses as I mentioned. We are going to show you a few screens how it works. So this is the main page of SDC SAM. As you can see, there are already a few assets that we are analyzing, and you can click on one of them and to check basically what are the details. So let's click on the last one, and this is the wind engine support. As you can see on this asset page, we have some information regarding the structure itself, what it is, where it is located. You can even preview it on the map. And you can see the general status of the structure, whether or not the parts, the items inside of the structure are in good condition, in fair condition, in poor condition, or in critical condition. Critical condition means the utilization factor from your performed analysis exceeds the allowable limit. Over here, you can also insert some real-life pictures or some FEA model pictures and so on. Then if you move from overview to components section, you are going to see that this entire structure is divided into some subparts. These are the components. So as you can see, this jacket structure is divided into 4 vertical legs, and then you have I think 12 horizontal beams. So you can nicely preview it over here and again check the general status of it. You can dive more into deeply because again these components are then divided into parts. So if you click on the part, you are going to again be brought more deeply into this specific leg. So we are analyzing this leg, and as you can see, again it consists of 9 total subparts. What I didn't also mention, for all of this, you can also preview what is the total maximum utilization factor for all of these parts, and whether or not the status right now is in which condition right now. You can also see where the last action was, when the last action was performed, whether it was some inspection, some repairment, and so on, and how many days till the next action you still have. Okay, so we can dive more deeply into part 2, let's say. So we are going to check what sections are there. So let's click on part 2, and as you can see, And this part 2 consists of 2 sections. It is hard to see from this plot, but one of the sections, basically it means a plate. One of the plate, this is the tube plate, and the second plate, it is a stiffener inside that is welded to the tube plate. You can again investigate it more deeply and dive into structural items. And as you can see, when you are at the, let's say, bottom of this hierarchy, here you can see that what structural items are inside of this specific zone. So we can see you have welds with utilization factor 9.0, and you can see here they are represented. And you can also over here check the plots with the results specifically for this selected items. And also you have plates. On the left side, you can see this navigation tool. So you can see there we have all the components, and you can expand and navigate quickly inside of them. Check different parts, different sections, what sub items you have, and quickly move around. Basically, in this case, you can see the status is fair or good, so the condition. So basically, this parts pass the standard requirements, and you can see it over here as the tickets, as we don't have any tickets. But in case it is not that nice, and the utilization factor exceeds the allowable limit, we are going to have tickets created for the areas with overshoots. So as you can see over here, for one of the parts, we found a ticket was created since some overshoots were found. You can see them over here. It is where the connection of horizontal beam with vertical leg is. On the bottom, you can also check the plots of the results for this part. And over here, you can see what checks were performed. In this case, we performed ENT 3001 static stress check and fatigue damage check. And also at the bottom, you can see what was the history of this specific zone. So you can see first the FA analysis was performed, and then a visual inspection was performed, and in the near future, another visual inspection is also scheduled. If you are currently inspecting this specific asset and this specific zone, you can edit this ticket and basically report what is the outcome of your inspection, whether or not it matches the FEA results or not, whether this health status is good, fair, poor, or critical. You can measure some parameters such as plastic deformations, plate thicknesses, and so on, and store everything inside of here. And also you can schedule some. So for example, let's say that this zone is in great condition. It doesn't have any damage, as the FEA results would say. Here I could say that the health is great, measure my parameters, and schedule, for example, a next inspection in 6 months. And then I will be also informed when the next inspection is going to be required for this specific zone. Then the last page, this is the resources. Basically here, as you can see, you can store everything which is related to the project. You can store all the reports, FEA models, some drawings, some links, etc. So basically all your models, all your results, entire structure, conditions, and outcomes of performed analysis, you can directly access from your phone without needing to open laptop, open your models or 500 pages reports and so on. You can simply just go to the structure, check your phone, what is there to inspect, and basically review it. More or less, it is that's all what I wanted to discuss. Some of the last things that I would like to mention, that given all of these things that we just discussed, also thanks to the feedback of our customers, as you can see, SDC Verifier can greatly speed up the time and save you some time when executing the projects. So not only you save a lot of time on the hand calculations, you don't need to basically perform all the checks either in some Excel sheets or on paper. All the structural items are recognized automatically and so on. And also reporting is very quickly, since most of the stuff is already predefined. So you can treat it as very great time saver. Last, some rewards. What are the benefits of using SDC? As you can see, and as we mentioned with the SDC Verifier standalone, it is one in all solution, so you don't need to jump between softwares for different stuff. You don't need to jump between sheets to analyze outcomes of checks and so on. Everything is stored inside one software. You can perform multiple checks up to your needs. If you want to perform bolt checks, fatigue checks, strength checks, and so on, you have more than 50 codes to do so. Then consistent calculations. Updates are seamless across your model. What we discussed, in case some modifications, simply update your model. You can rerun the calculations, and there is no more work to do. You can simply regenerate your reports and so on. And yeah, regarding the reports, automatic documentation, a huge time saver, as we mentioned. There are some of the customers of SDC. So as you can see, we have over 200 customers worldwide, and yeah, basically a lot of companies already trusted us, and they are also from different industries, as you can see. Some last words. Feel free to check our YouTube channel, also our YouTube, not YouTube, but our websites, where we post a lot of tutorials, where this webinar is also going to be posted, some previous webinars, and all the information regarding the SDC software and some standards is going to be shared on these platforms. That would be it from my side. Thank you so much for listening. I hope it was a helpful and interesting topic for you. I will now check the messages. If you have some questions, feel free to ask them on the chat. I will try to help you and answer them. You can give me feedback on the webinar. And in case you have some questions, also you can either ask them right now, or you can text us at the support, and we will be glad to help you. So let me check the channel. Okay, I see there are some screen disappeared, but I see it was back. I hope it was only for a while. But if it was back, then great. Aman, no problem. I'm glad you were there. Petro, how SDC Verifier detects welds for plate model and for beam model? Yeah, nice question. So basically, how the welds are recognized, this is also related to the preparation of your model. So in order to recognize the welds correctly, first it needs to be properly modeled. And in plate models, the welds are recognized basically where the properties are intersecting. So everywhere where you are going to have elements that have different property ID, then SDC is going to read a weld between these elements. For the beam models, it is a bit more tricky because for beam models specifically, the weld is not recognized. But what you can do, and what I also did for this model that I was presenting during this webinar, you can recognize joints. So this is the location where the beams are intersecting. And then you can manually set up welds where you have these joints. And yeah, as I mentioned, you can also create these manual welds for the plate elements if you need to. But yeah, they are detected manually for the plate model. It comes down to proper modeling of your structure. Does SD Verifier work with solid elements? Yeah, it also does. The weld recognition also works correctly with FEA, so you can use any type of elements and you should be good. I hope the flawless integrity of connections is nicely ensured. Yep. If there are any more questions, feel free to ask. Thank you, Samuel. Thank you for your time, and thank you for your feedback. I'm glad you enjoyed it. Are fatigue calculations only done using the number of cycles, or can a time series file be used as input? No, right now only a specific number of cycles have to be inputted. Thank you, Kola, for your time as well. Thank you, Michelle. Thank you. No worries, Joseph. Okay, then if there are no more questions, I propose to end this webinar. Thank you so much again, everyone, for joining, for listening and attending. Do you plan to include time series fatigue in DNV in the short term? Nathan, to be honest, I am not that aware of it right now, but I will ask the developers what we can do with this, and we can get back to you. Or you could, for example, write an email so we have a contact to you, and we can then respond answering this question. Since I'm not aware right now, I would have to contact with my developer team. So feel free to drop us an email on the support, and for sure we will get back to you. Thank you, Nathan. Okay, then, if there are no more questions, or if some questions will appear, you know where to reach us. Feel free to contact us. We are there. We are ready to help you. And once again, thank you so much for listening, and have a nice evening or day, depending where you connected. Thank you, everyone. Yeah.